Alright, so when it comes to applied electricity, the KVL and the KCL and the KVL themselves, they are not said. The concept on their own is not, they are not useful, right? But the main aim is that like we apply it in the circuit analysis. So whatever that we do in applied electricity is about circuit analysis, okay, magnetic or electrical or whatever. But they on their own, they are not that important. But the application is what makes everything helpful, like easy. It makes our lives easier. So one thing about the KCL is that we are talking about in this case. Then again, I'm repeating this. Everything about applied electricity is about this equation: V is equal to IR, right? Ohm's law, right? And then whatever it is that you talk about goes around this equation, right? So in KCL, our interest is what? Current, right? So we are talking about I here. In KVL, our interest is what? Voltage, right? One thing about the KCL is that whenever we are moving, whenever you're having a circuit, our interest of what is moving is the current, right? So in this particular case, which is the KVL, saying is that in the KCL, everything that we talk about, or every movement that we talk about is in terms of node, right? Our interest is how current move in nodes, right? Let me write this again. So everything that we do in KCL is about the current moving, right? So current, let me write this. That's for current, I, right? And then for KVL, everything that we do is more about the voltage, right? How the voltage moves and the concentration on the voltage, right? Yes. But then again, we talk about KCL, we are like whatever that we are doing here is about current, right? But then where is the current? What do we focus on in order to talk about the current? When it comes to KCL, what we are talking about most of the times is node, right? And I think we talk about this. A node is a point within a junction within a circuit where there are more than one wire. So when you look at this one, for instance, it's actually a node. If it to be something like, let's say this, let's say one branch, let's say A and this is B. This particular point here is actually, if there are two different wires, this particular point here is a junction, right? But because there are more than one wire, 1, 2, I think 6 or so, this place is a node, right? So when it comes to KCL, our interest is current at nodes. But when it comes to KVL, our interest is voltage within a network or a loop. Okay. A loop. Then again, these laws on their own are not that important, but they help us in the analysis of the circuit, right? Yes. So looking at this one, the KCL is like because our interest in the KCL is node. At a particular node, the total sum of the current leaving and entering the node is 0, right? Or we say the algebraic sum of all the current entering and leaving the node is 0, right? So looking at this one, you see that we can find a way to this is the total sum of the current entering, right? So I1, I2, I3. So what are they? So entering, let's use green. See, so we can see what's happening. So entering, right? I1, I3, right, and then I5, right? When it comes to those leaving the node, we have I2, I4, and I6, right? So then this is the sum of all those entering, the sum of all those leaving, right? But we can equate. The reason why we say the algebraic sum of them is 0 is that we consider the algebraic there means direction. So like looking at this whole thing here, the algebraic sum, this will happen. So this law can be stated in another way to say that the algebraic sum of the current entering and leaving the node is 0. So we can, this is what it means by the algebraic sum. Cyber of this is what it means. So 2 plus 2 is entering, right? And the most of the times we use a convention. You can say that those entering are positive, or those leaving the node are negative, or those entering negative, those leaving are positive. It depends on you. But here's the case where entering, let me do this. Enter implies positive, and let's see exit implies negative, right? So I'm entering. So I'm entering, I have 2, I have 3, what again? And then I have I, right? And then those exiting, right? Which ones are exiting? We have 7, right? If that exiting means negative, right? So negative 7, right? And then 4, right? So negative 4. And if I equate everything here to 0, that's what we mean by the algebraic sum of the current entering and leaving a node is 0. That's what it all means. Yes. Let me go smaller so you can see what's happening. So that's what the algebraic sum means. That the algebraic sum of the current entering and leaving the node, which is this side, is 0, right? Everything here can be arranged to come to this form, right? So it's the same thing. So you can just put those entering on one side, those exiting on one side. So those entering, these ones, right? So 2, 3, and then we have what? I, right? Those exiting, we have 7, and then we have what? 4. So you see, it's the same thing here. Just that you have to get the concept that the algebraic sum for this particular law, the KCL, now we are dealing on the KCL, right? The algebraic sum of the current at an entering and exiting a node is 0. So is this one. That can be rewritten to this form. It's the same thing, okay? So in the end, helps to get your I. Very simple, right? So that's 11, right? It's 4 and then minus 2 plus 3. Minus 2 plus 3, right? That's 11 minus 4, 5. That's 6 amperes, right? Then again, just by the way, but the units are very important. So that's what the case here is about. But it's not every time that you see it this way. At times you see it in actual circuit that you have to analyze, right? So you see, looking at this one, you are trying to find the I, right? There's the I, right? So even without writing anything, you can look. These are the ones exiting, right? Sorry, exiting, right? So if exiting and these ones are entering, yes. So let's say this time I'm making it this way. You're trying to see that it still holds. Let's say I'm making those entering. If you're entering, negative, right? Negative. And if you're exiting, it doesn't matter. You have to just be consistent with the convention that you are using, positive. So those exiting are what? 2, 2, and then 7, right? And those entering are what? 3, I, and 4, right? So we have 3 plus I plus 4, right? So the I will be equal to what? This plus this is what? 9, and then we have minus 3 minus 4, that's 7. That gives us what? 2 amperes. So you see, the same thing. You just have to be consistent with the direction that you use or the convention. So this here is just like a convention, right? You just have to be consistent with whatever that you are doing. So in actual sense, first of all, we're doing all that to understand the concept, right? But the main thing, we are not the case here. But the main thing is to understand, to see what's actually happening. So here's the case. So we're like, for the case here, we are doing current. Our interest is current, right? And then where are we focusing? At nodes, right? But for the KVL, our interest is what? Voltage. And we are focusing on what? Networks or loops, right? We want a complete loop. We want to describe how the voltage is moving. Yeah. So this one again, the algebraic sum of voltages. So you see, of voltages. So the voltages are interest, and what are we looking? Loops, a closed path, or network equals 0. So that's what it means. It's just the same thing. And then you see, when we're doing the KCL, we're doing it this way, that we put those entering on one side and then we put those exiting on one side, right? When it comes to the KVL, to make your work interesting and then easier for you, this is what you can do. Because we are like, our interest is V here, meaning that we'll be dealing with the whole of equation of V is equal to IR, right? It will be much more easier if you put the voltage sources on the left side and then the loads on the right side like this. Okay, that's just by the way. You can do it any which way, so far as it works for you, fine. But just choose a convention and then stick to it. That will make your work easier. So this one, the algebraic sum of the voltages in the loop is 0, right? So let's go over this and see. Then again, because here we are talking about loops, let's go back. For the KCL, because we're talking about current, what we can do is most of the times we use letters to represent the node, right? So I could have just said there at node A, and I do this analysis, everything here, right? All these equations, right? But when it comes to the KVL, because our interest is loops, or our interest are in loops, or like in complete closed path on networks, we actually use letters at the junctions, at the nodes and junctions again, not to describe the loop, right? So you see, this one is A, B, G, H, E. So this is A, B, G, H and then back to A. It must start from a letter and get to that letter. That makes it a complete loop. Then again, this naming here is just a description. So far as you get the right equation, you are fine. But this labeling here, or the name of the loop, is just description to help you see what's happening. Okay, so this is what I say. The algebraic sum of the voltage sources, the voltages in the loop is 0. So this is what loop A, B, G, H, E. So A, B, G, H, E. Right. So we start from here, come here, back to where we started. Right. So that's what it means. So what does it mean when we say the algebraic sum of the voltage in the loop is 0? This is what we're saying. That when we take a particular loop, now that we've taken this loop, you see initially I was saying that it is better if you put the voltage sources on one side and the loads on the other side, right? So this is the loop we are considering, right? Our interest is here. Let me use this one. Our interest is here, right? So looking at this, how many voltage sources are there? 1, right? And then again, when we go to the KCL, remember that we're talking about direction, right? The same thing here. You have to choose your direction and stick to it. The general way is to choose the direction that has been given. If it has not been given, fine. You can choose to move from the positive side of the voltage source to the negative side, right? So you see, this way. Are you okay? As if we're to be in the loop this way and come back to the negative terminal, right? Yeah. Let me write it here again. So voltage source, the long bar is a positive terminal, the short bar is negative terminal, right? So natural sense from here to here, right? This is how we are, the conversion that we are using. Okay. So now let's continue. And we are like the algebraic sum of the voltage in a loop is 0, right? So this is the loop that we've chosen. How many voltage sources are there? 1, just this, right? Then again, we are going by this equation, V is equal to IR. When you go by it, it's something you know already, so it makes your work more comfy, more easier, right? Voltage source just 1, so I just write it here, which is what they've done, right? And now we look at the loads, right? Anything that will use current within the loop is what we call the load, right? This is just revision. How many things are using current? This and then this, right? So per this particular circuit, we have one voltage source, right? We are going by V is equal to IR, right? How many R do we have there? 2. So we go with the first one. For this R1, what's the current passing through it? I1. So this is how we write it. I1, R1. The same thing here, right? And then what's the other load in this circuit? This ABGHE is R3, right? So R3, what is the current flowing through that R3? I3, right? So that's it. This is what we mean by the algebraic sum of the voltage sources in it is 0. So just like how we're doing for the KCL, we can move it and then bring it here, and then make sure that 0 that we are talking about in the law appears. So it could be something like this. We can write it this way. Let me read. So see what's happening. So, come on. So V1 then it's actually supposed to be a minus. So minus I1 R1 minus I3 R3 all is equal to 0. So this is what we mean by the algebraic sum. The moment you say the algebraic sum, meaning that we are choosing a convention, right? That those moving in a particular direction are positive, those moving opposite to that particular direction are negative. Then the algebraic sum is 0. So it's the same as this thing. The same thing, no difference. Just that the direction is what makes one of them one group positive and the other group negative. Okay, yeah. So the same thing here. When we choose this particular loop, let's see. Now we are here. A D E H E, right? What is it? A D E H and back to A, right? So looking at it, how many voltage sources do we have there? 1 and 2, right? You can choose any which way. You can choose to write it this way or this way, right? How many voltage sources do we have? This and then this, right? So looking at them, though they are voltage sources, if you are writing it in this form, the voltage sources are 2, right? Let's put them, we write in both ways. So the voltage sources for V1, so let's say now we choose to make our direction this way, right? This is the convention we are choosing for this particular loop, right? So V1. when we try to move to the other voltage source, you see that this voltage source is moving the opposite direction to this one, right? So we just write it this way and then write V2, right? So we are done with all the voltage sources in that particular loop, A, D, E, H, E. Now we go to the load. How many loads do we have in this particular loop? This is what we have. We have 1, 2, and then 3, right? And then remember, this is the direction that we've chosen, right? So looking at this one, R1, the current flowing through it is actually in this direction, right? So just the same thing. So I1, right? R1, right? Let's make it smaller so we can write everything there. I1, R1, right? What's the next load? Now we are done with this one, R2, right? Looking at the current passing through it, this I2 here is still in the direction that we've chosen, right? So this one will end up being, so the same direction, so it's a plus, right? So it is a plus. So plus indeed. So plus, what do you have? I2, R2, right? We are done with this voltage. Sorry, this load. The next load is which one? This one. Looking at this particular R4, what's the direction of the current? Right, it's opposite to the convention that we've chosen to use, right? This way. So it will be a minus, right? I what 4 R4. The same thing. It is this one that we arrange to come and get the algebraic sum is 0, right? So this is what happens. I1 V1 minus V2, right? And then you have minus I1 R1 minus I2 R2, right? Plus I4 R4, right? Equal to 0. This is the algebraic sum something. But if you want to go by this V is equal to IR, fine. Whichever one that works for you, just go by that one and you'll be fine. Right? So that's all about the KVL. Then again, the KVL and the KCL, we don't use them in isolation. Most of the time, we use them to analyze a circuit to see what's happening, right? So we don't just learn that one on its own and then go away. So you see, another loop, right? C, B, D, F, C. What is that? C. What is C? This C, B, G, F, and C, right? So the direction can change. Still the same thing. It could also be B, C, F, G, B. It's still the same loop because we still consider here, right? That's just by the way. So that's what we are doing. Now they are doing the algebraic sum. Looking at the equation here, you can see that they are actually doing algebraic sum. Oh, not algebraic sum. It's like they've grouped all the voltage sources on one side. So in this particular loop, looks like they are going by V is equal to IR. Per the equation that they've written here, there's no voltage source, so 0, right? And now, looking at what they've done here, the I2 is negative. What is I2? If I2 is negative, meaning that the conversion that they've chosen, even per the lettering here, because they went in this way, CBGFC, right? CB, so the conversion is this way. So, R2, right? What are the loads in this particular, let me use another color. The loads in this particular color are the R2 and R3, which are these ones, right? R2 and then R3. And this is the convention that we've chosen, the direction, right? So R2, the current flowing through it is in this direction, so it's opposite, right? So negative I2, R2, right? And then for the R3, right? Oh, there's another voltage load here. So R3, the current is in direction to the way we are moving, right? So positive. Then R5 is in the direction to what we've chosen, right? So positive. So this is it, right? And then another one. Now you are choosing ACFHE, right? ACFHE. What is it? ACFHE. ACFHE. So this is ACFH and then A. So this is the loop that we are using, right? A. What is it? So per the lettering, they are going in this direction, right? Okay. How many voltage sources are here? 1, right? Let me see that. Just one voltage source, just this, right? So then again, you are using this V is equal to IR. You can choose any which one. You can do the algebraic sum, or can do V is equal to IR. So the voltage source just one, V, 1, right? Then we move to the loads, right? The loads are 1, 2, and then 3 in that loop, right? Now the current flowing through this I1 is in the direction to the convention that we've chosen, which is this way, right? So it's a plus. We are done with this one. This one, R2, the current flowing through it is in direction to the convention that we've chosen, or the direction that we've chosen, positive. We are done with this one. R5, looking at it, so we see what's happening. R5, right? This is the direction, and the direction we chose was this way, so it's in opposite direction, so negative, right? Yeah, so we are done with this one too. So base go to R, that's what we're using. Write it the way that you are comfortable with, right? So this is actually an application of the KVL and the KCL stuff. Okay. And then this is the question. This particular one is saying that find the current in all parts of the circuit below, right? So looking at it, our interest is this, and then this, right? And then because let's go back. You see one time where like for KCL our interest is current, for KVL our interest is voltage, right? So when we are doing something like this, it means that because we are seeing current here, we can do some KCL analysis, right? What we can see about this particular diagram is that looking at the direction, you see this one, so looking at it means that our interest is this node, right? At node C, right? So at node C, you don't have to write it, but let's see. It's just for you to identify and see what's happening. Node C, right? At node C, you can see that this one enters, this one enters, this one is leaving, right? So if you do algebraic sum, or those, let's do those entering, exiting. So right now, entering, you don't have to write this, just by the way. Those entering are what? Let's see, positive, right? Those exiting are, let's see, negative, right? So looking at it, the ones entering are I1 and I2. So I can do this, I1 plus I2, right? And then I3 is exiting, so this way. So this is the algebraic sum, right? If we do one direction, the other direction on the other side, this is what we can do. It's just like rearranging this one. So it will be I1 plus I2, I2 is equal to what? I3, right? So it's like just the same thing rewritten another way, but it's like the same concept, right? Here we are writing those in a particular direction here, those in the opposite direction here. It's just the same as this, right? So yeah, that's what we can see about these three currents. Because we are talking about current, that's why we are using the KCL. So in this case, what we've written here is based on what? KCL, right? Then right now, what we are supposed to do is to actually find this current. If we have this equation alone, we can't find the current, right? So this is what we do. We can do some loop analysis, right, to see what's actually happened to help us find the current. So let's say in this case, I've chosen to use this BCDAB, right? This is the loop. If I choose this loop, now I can look at these two ones and then create some equation, right, to help us, because we have three. Then again, let's revise on our math. Whenever you're having three unknown variables, you need three equations, right? When you haven't, let me write it, three variables, we are trying to find the unknown, right? This is just by the way, the unknown variables. When we are trying to do this, if you have two unknowns, implies that you need two equations, right? If you have three unknowns, you need three equations. So four unknowns, four equations, one unknown, one equation. So yeah, that's what it means. This is just by the way. Let me see. So right now we have one equation available, right? So what we are trying to do now is to what we are trying to do right now is to get, because we have to find all the currents, right? And the currents are I1, I2, I3, and then I2, right? So meaning we need three equations. Right now we have only one equation, so we have to get two more equations in order to find what we are doing. So now we've chosen one loop, we have one equation, which is this one. So this is equation 1. Let's try to be beside it. 1. this is 1, right? So we are trying to generate equation 2. So because we want equation 2, we are using, you can use any other loop that you want. Okay, so we are using this loop B C D A B. This is it. Let's write it here. Right. So looking at this one, how many voltage sources? Just one, right? I'm writing by V is equal to IR, right? Voltage source is 1, right? The loads are these ones, right? So 2, right? So 2, and then the current is what? I2. Oh, that's 1. And then, because there's a positive terminal, there's negative terminal, so this is my conversion. I'm choosing this direction, right? And then this one too is in the same direction, right? So the resistor is 8, right? And the current is what? I3. This is my equation 2, right? Let me write this equation 2. Equation 2. Now I'm trying to get equation 3. So let's see. Equation 3. So equation 3, let's choose another loop. Which one do you prefer? Let me choose this one. So let's see. Let me choose this loop, right? Which is then again, the loop now letters are just for identification. So I'm choosing E C D F E, right? So meaning I'm going by this conversion. How many voltage sources? Just 1, so 20, right? And then this one is in the direction towards I'm looking for, so 4 I2. This one too is the same direction, so plus 8 I3, right? Yeah. So I have 3 unknowns. You can go straight forward and then use a calculator. Yeah, if you have a calculator, it can be of great help to find just this one, just straightforward. Yeah. So let's see if we decide to find it just straightforward. 3 unknowns. And then when it comes to using a calculator too, there are ways that you have to what's the name? Convention that you must follow. I think I'm using convention a lot. You must follow in order to get what you are looking for, right? So let's see. Okay, equation. The calculator is getting complex for me.